Welcome to the tutorial for the Scale Model Lab. In this lab, we're learning to develop a sense of scale about the universe around us. We'll be making a couple of scale models, one of our own solar system, and the other of our local group of galaxies. As we do this, we'd like you to reflect on just how far apart things are in space. The purpose of this tutorial is to show you what you'll be doing in this lab and to help you understand how to do this yourself. This lab is based on the ideas from the online lecture 01A Introduction, so you should make sure you go through that as well. We'll review a few of the key points here, but you definitely want to view that lecture to get a full understanding of the idea. A scale model is a small model of a larger object or system. To be a scale model, it has to keep the proportions the same. So if one dimension gets smaller, the rest get smaller by the same fraction. A globe is a scale model of the Earth. Here is a scale model of a fictional spacecraft. In this lab, we'll be making two different types of scale models. The first one, based on our solar system, will be pretty big, so you're welcome to do that one just on paper. Though if you want to set it up for real, you can go ahead and do that too. The second one is based on the group of galaxies around us known as the local group. In this case, we've shrunk the scale down so far that you can fit it into a room. This one you should definitely make yourself and take a picture of it if you can. Our solar system consists of our star, the Sun, and the planets and other smaller bodies that go around it, including the Earth. If we want to shrink the solar system down to a manageable size, we're going to have to make it 20 billion times smaller than its real size. On that scale, the Sun is just 7 centimeters across, about the size of this orange. The largest planet orbiting the Sun is Jupiter. On the scale we're using, Jupiter is only 7 millimeters across, about the size of this bead. The Earth is less than 1 millimeter across, about the size of a grain of salt. And the Earth isn't even the smallest planet. Table 1 in the lab packet lists the sizes of all the planets, along with the dwarf planet Pluto, so you can see their sizes in our model. Table 1 also shows you how far apart you have to put the planets on the scale we've set. Notice that Table 1 gives two columns for distance. One is the real distance expressed in astronomical units. An astronomical unit is the average distance between the Earth and the Sun. The other is distances for our particular model scale. So if our Sun were about the size of an orange, the Earth would be just over 7 meters from the Sun, or about 25 feet. Pluto is almost 300 meters from the Sun, which is close to 1,000 feet. In this part of the lab, you should start by getting a scale map of some place of interest to you, like these maps of Citrus and Chaffey colleges. We recommend using a place you know well. One of our goals here is for you to be able to relate this scale model to your own surroundings. You can use an already existing map or print out an online map. The map should have a scale on it, preferably listed in meters. For online map programs like Google Maps, you can change the units by clicking on the scale. Have a closer look at the scale bar on this map. It says 50 meters. That means that the line shown here represents a distance of 50 meters on the map. Since the whole map is around 10 times the size of this line, it shows you about 500 meters across the college campus. Since the whole scale model is 300 meters across, you want your map to cover an area that is at least 300 meters and up to 600 meters across. Now think about how big each of the planets should be. Remember that the Sun is the size of an orange. We don't mean an orange sitting on the piece of paper. We mean an orange sitting on one of those walkways in the campus. Imagine you had set an orange down on the ground on the campus, right before they took this aerial picture that forms this map. That's how big the Sun would be on this scale. Really tiny. So on this map, you'll need to mark the locations where you should put the Sun, each of the planets, and Pluto, without worrying too much about how big they are, since they're all just little dots on this scale. Use the scale bar to help you figure out how far away to put the planets from the Sun. For example, if the scale bar is labeled 50 meters, and Mercury is only 3 meters from the Sun, then Mercury is going to be less than 1/10 the size of the scale bar away from the Sun. As you look at the distances on the table, notice that the first few planets are all very close to the Sun, while as you get further out, the distances between the planets grow. You can assume the planets are all in a straight line, though in fact they never really line up this way. Once you've got all the planets clearly labeled on the map, go ahead and take a scan or picture of it and include that with your assignment. There are also a few questions in this section of the lab. Make sure you know the definition of an AU in question 1. For question 2, you just need to check to make sure you're using the same units on the map as are given on the table. In question 3, have a look at the sizes of the objects and decide if the dots you're making on this map are to scale or not. And is it even possible to make dots the right size to keep the same scale as the map? While marking up your map is a required part of this lab, you're also welcome to try making a solar system model out in the real world, using your map as a guide to where the planets go. Feel free to use household items for the Sun and planets, but try to get them close to the right sizes. This is a fun project to work with friends and family on. Even if it's not practical to set up the whole thing, try making part of it with just a few planets and the Sun. The stellar scale is the next step up in scales. It's the distance between the stars. On this scale, we work in light years rather than AUs for distance. A light year is the distance a beam of light travels in 1 year. This is around 60,000 AU, or 10 trillion kilometers. We're not going to make a stellar scale model here, but it's good to know that the nearest stars to our solar system are about 4.2 light years away. If we use the same scale we did for our solar system, that nearby star would be about 2,000 kilometers away. Remember that 1 kilometer is 1,000 meters, so this is 2 million meters away. Have a look at some online maps again and see if you can figure out a city that is around 2,000 kilometers away from where you are now, and list that here. If we want to make a model that includes anything as big as a galaxy, we're going to have to change the scale. While our solar system has just 1 star in it, our Milky Way galaxy has hundreds of billions of stars spread out over a diameter of 100,000 light years. So our first step is going to be to shrink everything we've looked at so far by another 500 billion times. On this scale, the entire solar system is about the size of a single atom, and our galaxy becomes small enough to fit in your hand. This makes it small enough that we can fit the Milky Way's neighbors into a single room. This group of galaxies is known as the local group of galaxies, and our galaxy is one of the biggest members of. Table 2 lists the data for the Galactic Scale model. We'll use our own galaxy, the Milky Way, as the central point and measure from that. Start by cutting out circles of paper in the sizes listed in the last column of the table. In reality, not all galaxies are shaped like circles, but many are, so that's a reasonable place to start for this model. Note that 1 inch is about 25 millimeters, so if you don't have a ruler marked in millimeters, you can convert the sizes to inches by dividing the numbers in the table by 25. Also note that the smallest 2 galaxies on the list, Leo 1 and the Tucana Dwarf, are small enough that it's probably easier to just draw them on a small piece of paper. You might lose them if you try to cut them out. As you cut out these circles, make sure you label them so that you know which galaxy is which. If you have colored paper, that makes it easier to distinguish them as well. Remember that each of these circles represents a galaxy, a collection of billions of stars. Our Sun is in the Milky Way galaxy, about halfway out from the center. To lay out your model, start by putting the Milky Way in the center of the room. We'll use the right ascension data to determine which direction to put the other galaxies in. Pick one direction and call that 0 hours. Then the opposite side will be 12 hours. Notice that if your room isn't very big, then you might want to put the Milky Way closer to the 12 hours side of the room. The most distant galaxies are roughly in the 0 hours direction, so you'll need the most room in that direction. Combine the distances in column 4 with the right ascensions in column 2 to decide where each galaxy goes. For example, the Large Magellanic Cloud is only 0.16 meters, or 160 millimeters, from the Milky Way, in the 5 hours direction. This is almost at right angles to the line between 0 hours and 12 hours. Note that if you don't have a meter stick or tape measure marked in meters, you can treat 1 meter as the same as 1 yard, 3 feet. This introduces a small error in the distances, but it's only about a 10% difference in size. When you finish setting up your model, take a picture of it or make a sketch based on what it looks like. As you look at your model of the local group, keep in mind that all of these things are moving. Over hundreds of millions of years, these galaxies orbit each other and move towards and away from each other. As they do that, how likely do you think it is that they might hit each other, especially compared to the scales we saw earlier in the lab? Your teacher will let you know where to submit the lab materials. This will include the questions in the lab write-up, your solar system scale map, and your picture or sketch of your galactic scale model. Also note that you're welcome to work with 1 or 2 other people on this lab if it is practical for you to work together. However, make sure you each write your own answers to the lab questions. You also have other ways of getting help on the lab, including asking your instructor for help. Your instructor will let you know what their schedule is and how you can best keep in touch with them, and what other help tools they've made available for you, such as discussion boards. Finally, remember that this is just the first half of the Scale Models Lab. We'll be doing more with the data in this lab next time around.